Right, so final talk of the day is by Katherine McLaughlin from Oregon State University, talking about analysis of networks with missing data.
All right, great. Thanks for having me, everyone. Thanks to the organizers for inviting me. So there's a little bit of a story behind this, which you may have realized. I am neither Mark Hancock nor Krista Guile, who are the two co-authors on the paper. The citation is here on the bottom, and this is work extending from a more theoretical version of the same paper published back in 2010. So both of them send their regrets that they could not be here, and I'm going to try to do justice to their work. I have background working with both Mark and Krista, thinking about a type of adaptive network sampling called respondent-driven sampling, which is used to access hidden populations. So I'm not going to go too much into that, so I can spend time on this talk here, but if anyone is interested in more specifically what I do, I'm happy to chat offline or over dinner. All right, so I just finished up my PhD about 2 months ago, working under Mark at UCLA, and this fall, and then moving to Oregon State to start as a professor there. And what I want to do with this talk is shift what we've been thinking about throughout today a little bit, and instead look at the process of gathering information about our network, and more specifically the fact that we often only partially observe our networks. And the application for this work is the National Longitudinal Study of Adolescent Health, or AdHealth, which we've heard a little bit about today. So an overview of what we're trying to do, we say that we have a network of social relations. So it's a little bit easier to define than some of the things we've been thinking about earlier today. We're going to think of the nodes as people, and for AdHealth, the ties between them are friendships. And we want to represent the structure in this network by saying that it is a conceptualization, it's a realization of a draw from some network model. And the reasons that we may only partially observe this information could be due to a known sampling mechanism. So it may be too cost prohibitive or difficult to do a full census of the network, so we sample from it instead. Or secondarily, we may have some unknown missing data mechanism. Even if we try to conduct a census, some people may not respond to our questions. So given that we have these partially observed networks, we want to try to develop a framework to handle missing data. And this comes not from reinventing the wheel, but from building on other work in the areas of missing data, network sampling, and network modeling. And what I'll try to convince you of over this talk is that dealing with missing data can be done routinely by using models, and we don't need to use some sort of ad hoc, non-model-based approach, which could be prone to error. I'm going to give a little bit of background now about the AdHealth study before returning to this at the end in the context of demonstrating the model and also talking about some methods of goodness of fit. So it's a school-based study looking at health-related behaviors for kids in the U.S., grades 7 to 12. So the application here is going to be looking at one specific school. But for all of these schools, the children were asked to nominate 10 friends, 5 boys and 5 girls, and we also collected some demographic and behavioral information about them. Here's an example.
Just out of interest, grade 7 is what age?
So grade 7 would be probably about 12 years old. And then, sorry, I said that the wrong way. Grade 7 would be about 12 years old. Grade 12 would be about 17, 18. So we're looking at them sort of through their teenage years. Okay, so here's an example of what one of these networks might look like. Here the nodes are the children. The number on the node is the grade that they're in, and the ties between them represent these friendship nominations. So we can see that there's a lot of clustering here within grade, which we would expect. This is shown for a larger network on the left here, where the color is the grade. On the right, the nodes are colored by race. So we again see these sorts of groupings. When we think about partial observation for these social networks, there are several different ways that this can happen. And so I want to make sure that I spend time going through both of these before moving on to the modeling framework. The first way we can have partial observation is through the sampling design. So, for example, we could be looking at a company, and we want to know the ties between people in the company, but we can't ask everyone for some sort of practical reason, so we say we're going to take a sample of 10% of the people and ask them about their collaborations. In the schematic here, we've chosen these two nodes shown in dark blue and then asked them to name all of their collaborations. This is an egocentric sample. We can also use an adaptive sample, which I'm going to go into much more detail about later, but the basic idea here is that from these two initial nodes, we then follow up and gather information about the people that they nominate and the people that they nominate. And so in this example here, we don't have any missing data shown, but we can imagine a scenario where we would have some. There's also partial observation due to out-of-design missing data. This is the case with what we're dealing with in AdHealth, where we do try to conduct a census and gather information from everyone, but people could be out sick, they could have a meeting or something and not fill out the survey. So for the schematic here, we tried to gather information about all the nodes, but the two shown in light blue didn't respond. And so when we think about what our network would look like, we have to remove all of these nodes and then also the nominations of these nodes by people that we did observe, so we end up with a network that looks like this. The last case that's listed here is a boundary specification problem where we're not sure what the set of nodes should be. For example, should a contractor be considered part of a company? And so this problem is beyond the scope of this paper. I'm not going to get into it in this talk, but this is another reason why we may have partial observation. So most of the analysis that's done in networks ignores individuals with missing data. So we end up with a scenario more like this one where we've removed some information that we did have. In particular, some of the nodes that we observed did nominate nodes who we do not have information on, but we remove those edges. So we're throwing away information which we don't like to do. So what we would like to be able to do is create some sort of framework where we can handle missing data. This builds on some earlier work, which was a bit simpler. One project was to assume and enforce reciprocity. So we say, if we think that all of the ties in our network should be reciprocal, and we only observe an in degree for one person, and then we do not observe that person, we should just assume that they would have nominated the other person back. This has a lot of problems if we are not dealing with reciprocal networks. Another approach was to treat respondents and non-respondents separately using a pseudo-likelihood approach, but this does not allow us to model structure between these two groups. Another approach is to fit simple network models with the non-observations, but again, these approaches are more simplistic, and we'd like to be able to come up with a more sophisticated method and also allow us to do some model checking. All right, so the 2010 paper that was more theoretic by Guile and Hancock spoke a lot about adaptive network sampling, so I'm just going to give a little bit of background on that. In this scenario, we assume that the population is joined by these social ties, and that researchers can access only some of the members of this population. For the sampling design, we begin with a reachable sample. These people are called the seeds, and it's often done through a convenience sample or something else that we kind of shy away from. And in respondent-driven sampling, which is what I do, we have to use a convenience sample. We then extend the sample by sampling the people that are tied to those who are already in our sample. So this uses information that we collected during the survey to direct our subsequent sampling. But we note that the sampling design only depends on the data that was observed in the sample. There are some concerns for this approach. Firstly, dependence on the seeds that we selected, confidentiality, especially in the case of RDS, respondent-driven sampling, which is what I do. We're dealing with hidden populations, so it may be very difficult to get them to participate. The question of whether we can do estimation at all if the sample depends on this unknown network. However, adaptive sampling also has some strengths, which are listed here. I'm not going to go through all of these or expand on them for time, but what we would note is that it allows us to conduct a network sample in situations where it otherwise would be difficult, and we can adjust during the sample for some of these discovered features in the population. There are also some issues with implementation, notably that these link tracing designs can be challenging for privacy reasons, for logistical reasons, and questions about how to choose the seeds, which people they should be, what proportion of your sample should be seeds, are all things that a lot of literature has been written on. To give some examples of when sampling is adaptive, in the case of an individual sample, if we choose our sample based on observed covariates like race or sex, that's an example of an adaptive sample. So is link tracing, if we're following up based on these known covariates. And the last bit here, if we link trace with probability proportional to the number of partners, so a person's degree, that's also an example of an adaptive design. Things that are not adaptive, which can also think of as sampling where the people we do not observe are not missing at random. Examples are an individual sample where people are selected based on unobserved covariates, so things like infection status or illicit activity, or link tracing designs, again, where links are followed based on these unobserved properties. All right, so now let's get into some statistical models for social networks. This should be pretty standard, and I don't need to go into a lot of detail for this audience, but we start with a set of n social actors, and we want to look at the relationships between them. So we say that there's a tie, Yij is 1, if there is a relationship between them. We have a graph, we're going to let x be our covariates, and what we want to try to model is the joint distribution for the covariates and the network structure. Okay, so if we completely observed x and y, so in the case where we do not have partial information, then we would want to do inference for eta, these are the network parameters, based on this likelihood here. But this is complicated because we have this partial information. So we think of now two types of data. There are the relations and the covariates, so these are the x and the y that we observe, and then there's also indicators of the relations and covariates that were sampled. So this you can think of as the design here represented by D. So when we write down the joint likelihood for eta, which is the model parameter, and psi, the sampling parameter here, we note that we are explicitly stating which parts are observed and unobserved. And we have good ways of thinking about how to write down models for the second term, and the framework that we want to do is ask, when can we ignore the sampling process? So ignore in quotes should ring some bells for you. And when we think about this, we're regarding psi, that's the sampling parameter, as a nuisance parameter that adds complexity. And so we want to consider when we can just use what's called the face value likelihood here, which will be the second term. So for these class of adaptive designs that I've been talking about, we say that it's adaptive if we can sort of get rid of this missing information here. So that's saying that the sample only uses information collected during the survey to direct subsequent sampling. And it only depends on the data that we do observe, not the data that we do not observe. So what we do not observe is this z miss here. And in particular, these adaptive observation designs satisfy the missing at random condition of Rubin for thinking about missing data. So the result of all of this is that we can look at standard network sampling designs, such as conventional single wave or multi-wave link tracing sampling designs, as adaptive. And that allows us to create a sort of parallel term for ignorability for network models, which Guile and Hancock lay out in their 2010 paper. And this is called amenability. In particular, we say that the observation process is amenable to the model if it is adaptive and if the sampling parameters and the model parameters are distinct. And what this allows us to do is split the likelihood into these two parts, where the first piece here is the sampling design likelihood and the second piece is the face value likelihood. And if we have this amenability, then for the sampling design, we can ignore it in the sense that all of the resulting likelihoods we're considering will be proportional, and we can just consider models for the face value likelihood. So even if this is not true, even if we're working with an observation process that's not amenable to the model, there still are some things that we can do, namely that we have to model this first term. So I'm not going to say a lot about this here, but it is possible. But going forward, we're going to assume that for our partially observed data, we do have this missing at random assumption. And when I get to the end, one of the goodness of fit measures that I will look at will evaluate how we're doing with this assumption. For how we actually fit this network model, we use the ERGM framework. I think, again, for the audience, I don't need to go into too much detail here, but this is a very flexible framework that allows us to include a lot of both structural and covariate information about the model. So we have these eta, which are the parameters we're looking at, and then we also have these graph statistics, and we are going to do inference by trying to maximize this log likelihood function. This is done using MCMC for computational reasons. This is all in the ERGM package, part of the StatNet suite in R, so it's very easy to implement. All right, so now I'm going to show the application to the AdHealth data. This is the specific school that we're looking at. It's, I believe, school number 5 for anyone who has access. And one of the important things that I want to say is that the public version of the AdHealth data that's available already makes a lot of these sort of ad hoc missing data assumptions. In particular, what it does is say, for any students who did not nominate ties, in this school, only 70 of the 89 students nominated ties. So the public version of the data will delete all of the nodes that did not report friendships, which also deletes all of the in-ties that they receive from students who did nominate friendships. So the sort of public version of AdHealth already has a lot of these assumptions built into it. The private version, which is what we used for this analysis, gives the full information. Okay, so recall the students can nominate friends. Here the shape of the node is sex. The color of the node is their grade in school. These are all of the ties that are being deleted when we look only at the people who reported friendship ties. So in particular, this person here received a lot of nominations, but they themselves did not complete the survey. So all of these ties into them are lost. And so this is the version of the network which you would observe once all of those ties have been deleted. Okay, so when we want to go into a study like AdHealth, we have both scientific questions and methodological questions. So the scientific questions usually come from our collaborators, and they'll be interested in things like, do friendships form in an egalitarian or a hierarchical manner? From our own experience in school, we can probably tell that there are going to be maybe some popular kids and some less popular kids, but this is something that we would like to be able to back up with data. Methodological questions are things like, can we even fit a network model with missing data? So is this possible? And is this model going to be different at all from the model using just those fully observed individuals? Okay, so there's 4 types of dyads that we can consider. We have respondents and non-respondents. So this upper left-hand corner, dyads from respondents to respondents, are the ones that are included in what will be called the complete case model. This is the one that deletes the information about in ties to non-participants. But we also observe this upper right corner, which is nominations that people who did participate make to people who did not participate. And we do not observe either of these 2 other scenarios, although we do think that in the sort of complete network, there would be ties between these individuals as well. Okay, so to fit the ERGM model, the final model, and I'm not going to talk at all about model selection here, that's sort of a question for a different talk, but the final model that Guile and Hancock used had 21 different terms. They put in network structure terms like density and reciprocity, and then down here transitivity, which is indicative of a hierarchical structure, and cyclicality, which is indicative of a more egalitarian structure, and isolation, so students having no ties. And then they also added in covariates for popularity by grade, popularity by sex, and then these sort of differential age and sex mixing terms. So we can write out the sufficient statistics for each of these terms in the ERGM framework. I'm not going to do them all, although they are in the paper, but I just want to highlight 2. And in particular, this is to address the scientific question that we may ask. The left-hand triad is a transitive triad. So we can see both this person and this person nominate this third person, but that person nominates neither of them in return, indicating a type of hierarchical structure, whereas this cyclical triad on the right is more indicative of an egalitarian structure. And the sufficient statistics for these 2 terms are simply the counts of these types of triads in the network that we observe. All right, so I'm going to compare several different models. The complete case model is what would be available, again, if we deleted all of the in ties to non-respondents. That's the one that's commonly used. That's the one that you would get if you use the publicly available AdHealth data. So that's what's called the CC model from here on. The all observations, or AO model, is the one where we keep the non-respondents and we keep the in ties of people who nominated them. And something else to note here, for this particular network, we do actually have covariates on all 89 of these people because they followed up with the non-responding students in a later wave. But that may not always be the case. So we can see here the differences in structure. I'm going to focus on these two models. The paper also includes this incomplete case model, which uses those additional covariates, but not the extra tie information. And this was just done to assess whether any differences between these two models could be accounted purely in terms of covariates rather than network structure. The moral of the story is that no, it cannot. So I'm not going to spend a lot of time talking about it here. All right, so we fit our ergo model. We get a big output like this. I'm not going to talk through all of these terms, but you can kind of look for yourself. The ones that I want to highlight are this mutuality term. So we see it's significant and positive, which means that we observe a much larger number of mutual dyads than we would expect just due to chance. In terms of these transitivity and cyclicality values, we see positive significance for transitivity, negative significance here for cyclicality. So this is showing that we do have this sort of hierarchical structure that we might expect. And when we compare these two models, so these are, again, the coefficients and the standard errors, we're not seeing a lot of difference in terms of the sort of scientific takeaway message from this, right? Things seem to be significant or not significant in both of the models, but it's sort of not a fair comparison to make here. And so we need to do a little bit more digging before we can compare just the values here. So to compare these two models, what we want to do is see what the overall impact of erroneously using this complete case model when we really care about the full model. So to do this, we can calculate the Kovac-Leibler divergence of the two models when they're both used to model this smaller subnetwork that's used for the complete case. And in particular, so this is all done in the appendix of the paper, but the divergence is 159, which we know is pretty large magnitude. So the takeaway is that these two models are substantially different representations of this smaller subnetwork. But as I said, it's hard to directly compare these two approaches because the parameters are kind of on different scales. So instead, we're going to use the mean value parameterizations instead of the natural parameterizations, which puts the coefficients on the scale of the network statistics rather than this conditional log odds scale. So when we do that, the standard errors are left off here, but they're in the paper if you're interested. We see some more differences emerging between these two models. In particular, the ones that I've highlighted here, the complete case model has a much larger number of mutual ties and also a much larger number of isolated people. So these two models are finding some different structure in the network. And this is sort of motivation for why we want to be able to use all of the information that we have available. Okay, so we can also compute some goodness of fit measures. We don't know what the sort of true reference distribution is, what the solid black line is, so we compute it by simulating the unconditional model under the MLE. And so then the box plots show different draws from this network model, and we see that we're doing pretty good at capturing the out degree distribution, except in these middle ranges here where we can see that the model has kind of smoothed the out degree distribution a little bit more. We're doing good for in degree also, and the same thing for geodesic distance, which is the minimum length of the path between two different nodes. So these are just some kind of sanity checks that our model isn't doing anything crazy in terms of misrepresenting the degree distribution in the network. Okay, another goodness of fit metric that we can look at is the percent of possible realizations, or the percent of possible relations that are realized. And here, this is the same schematic I was showing before, where this upper left block represents dyads between respondents and respondents, and this is nominations by respondents to non-respondents. These are the proportion of ties that we actually realize in our school, and we would like the model, the all-observation model, to be able to reproduce these proportions. And the model also gives us proportions for what these other two areas would be. But what we see here is that we're not doing too great of a job, actually. These values are a little bit off. And this is a way that we can assess the missing at random assumption. So if the part of the network that was partially observed was missing at random, we would like to be able to explain this differential popularity by terms in our model. But here we see that we're not doing a great job of that. So to account for this, we add in another term to the model to measure this non-respondent popularity. And this will be called the differential popularity model, which is the all-observation model with the inclusion of this extra term. So what this term measures is the tendency for non-respondents to receive friendship nominations. And the sufficient statistic here is just the count of instances where this occurs. So when we add this term into the all-observation model, we get differential popularity values, we get percent of possible relation realized values that are much closer to what we originally observed. So we think that by adding this term into the model, we're more comfortable with the assumption that the data that we do not observe is missing at random. And this is a comparison, again, of the two fits of the all-observation model and the differential popularity model. And we see that we're not breaking any of the scientific conclusions here by adding in this extra term. And we observe the same sorts of more mutual ties than we would expect, and transitivity and cyclicality that's indicative of a hierarchical structure. So the scientific conclusions that we can take away from this model, as I said, we get more reciprocity. We also observe, I didn't highlight these numbers, but that males receive more nominations from other males than females receive from females. Nominations within grade are much more likely than nominations outside of grade, which we would expect. Nominations of older students are also more likely than nominations of younger students, which again, we may expect. And this is sort of consistent with our idea of a hierarchical rather than egalitarian structure. And then also we have more students being isolated than we would expect just at random, which again, maybe is something we would expect from having been in school. Okay. So now I want to just quickly summarize some of the methodology and provide a couple concluding thoughts here. So the challenge that we addressed was that in many instances we only observe part of a network, and we would like to be able to have an inferential framework where we can handle these types of data rather than having to make these sort of ad hoc decisions like just deleting rows of observations. So what we did is we fit a model to all of the observed data. This was the AO model. And we used information in the sample, such as the in-ties and the covariate information, to improve the model. There are some limitations with this approach. Firstly, we have to assume that the full network size is known. So in a case like AdHealth, this may make sense if we have a complete roster of students, but there are many other scenarios where we may not know the true network size. In particular, responder-driven sampling, which I do, we often do not know this. It requires identifiability of the alters. So if I nominate someone who did not respond and someone else nominates that same person, we have to be able to tell that they're the same person even though that person did not fill out the study. And then we also have this assumption of missing at random data. So as I said really briefly, even if we have missing not at random data, we can still attempt to impose some sort of model for the sampling process, but it does make it a little bit more complicated. Implications for study design: we get to collect and keep data relating to non-respondents, so in particular the in-ties that they receive. and any covariate information we may have on them from a follow-up study or a study that was conducted separately. For AdHealth, there was both an in-school and an at-home study. And we can also keep information on the number of non-respondents. And the big takeaway here is that we can still do a type of likelihood inference when we have missing data. So to provide some final concluding thoughts, we can apply network models to scenarios with partially observed data to address scientific questions about the full network. There are two different ways that I discussed here where we can think about partial observation. That's through missing data, as in the case of AdHealth, where people aren't filling out a survey, but we could also intentionally try to not observe everyone through some sort of egocentric or adaptive sampling. And here we can, in this framework, use both the relational ties, so information about the network structure, and the covariate information that we have about the people. And we don't have to do some sort of simple random sampling, so we can use these adaptive sampling methods. And using these pieces of additional information can improve our possibilities for inference. We can look at cases where we're not missing at random. We can use extra information to improve inference, and we can attempt to measure sample biases and also make some sorts of conclusions about the unobserved units. So I'm going to leave up some references here for the sort of variety of topics that I talked about, and I'm happy to do my best to answer any questions, even though, again, I used we a lot in this talk out of habit, but all of the credit for this work goes to Mark and Krista.
So obviously you use the ergom to do most of the modeling. Now the ergom is probably more has larger dispersion than your sampling allows, because your sampling is rather restrictive with asking for only 5 friends. Could that account for something of the lack of fit as well, or?
It might, I think. Although if we go back to so the out degree here, it is sort of capped at 10, which is what they use. So I'm not sure if they actually put some sort of constraint in the model or not.
It's probably capped.
But
it's not capped at 10, it's capped at 5 and 5.
Right, yeah. That's true, yeah. And that we notice that when we look at the in degree here, we do see, so for in degree people could receive more than 10 nominations. So yeah, that's a good point. I would go back and ask Mark about that. Yes.
Last time I made this remark, somebody got very angry. Missing at random is really very badly defined by Little and Rubin. It's a very good definition if you've got 2 variables. It's a very bad definition if you've got more than 2. You were in a convenient position because you actually had sex and grade, rather than age. How would you define missing at random? So you assume that things were either entirely observed or entirely unobserved. What do you do when you are in a much more interesting and complex situation where you've got complex patterns of missingness? How do you define missing at random then?
Right, so here we were thinking about missingness of potential edges, and we were treating all of the covariate information as known. It does get more complicated if we were to include many more covariates. So we could try, potentially some sort of imputation strategy there. We could try thinking about if the observations that we do not have could be explained by other variables which we do have.
Well, that was also, I'm just not quite sure of the logic. So you said the model didn't fit very well until you assumed that the missing people were not missing at random. You had to add in something over and above your known covariates in order to explain them. So I'm not quite sure what the concept of missing at random means if you're saying the missing links require an additional parameter over and above what we know. Is that a contradiction?
So the extra parameter that I added in did come from information that we had. So it wasn't this sort of over and above information that came from a different source. It was information that we would observe in the network. It's just that the earlier model, I hadn't included that term.
But the information that you observe is that people hadn't responded.
So, so this was using information about the nominations that people made to non-respondents. So that's information that would have been discarded in the complete case model, but which we did keep for the all observations model.
There is another case that you don't consider, I'm right, of missiness, is the inflation of nodes that happens when you don't identify names in a correct way. For example, if you do the sample of migrants and they know each other only through nicknames, for example. So maybe you name a person in a certain way and the same person is named by others in a different way. You assume that there are two nodes instead there is only one. And have you thought of that, or?
So that's sort of getting at this issue of identifiability, right? And so in that case, you're saying that instead of having some nodes missing, you're really having like extra false information that's added on top, so maybe more noise? Is that a way to think of it? Or, so yeah, I don't think that we've really thought about that in this context, but I think that that's something that would definitely be worth considering, and I will bring it back to Mark.
So, Katherine and Lincoln again. And,